So, hello everybody. I'm running a workshop today about how to build confidential EVM dApp with smart privacy. So, I'm Harry. I'm a technical product manager at the Oasis protocol. I'm handling the Sapphire EVM chain and the Oasis privacy layer. So, the workshop slides are available. If you want to get your laptops out or scan or whatever, you can run through them with me. There's going to be lots of code examples. And lots of really, really useful stuff if you do want to try and build some stuff. So roughly, we're going to go through smart privacy, confidential EVM, how's it different, getting started with building apps, then some examples and some cool stuff, I hope. So what is smart privacy? I think this is a good place to start, which, how many of you are like privacy maximalists? So you're all privacy, no transparency, right? But what about transparency? Because everything on EVM is transparent, right? But realistically, like the rest of the world exists in between where we need privacy and we need transparency. So think of like if you're sending an envelope to somebody, you want the inside of the envelope to be private and the outside to be transparent. And at the moment on EVM, that's just not possible. So there's a lot of sort of different use cases for this. So like if you look at the use case of ZK, you're providing proofs that you know are secret, or you're having transparency but only within select groups, or conditional access control. So you want to be able to gain access to something but only if you know the secret or someone's given you access. So fundamentally, smart privacy is conditionally controlled by the smart contract. So rather than the protocol being all private, the contract gets to decide what is and what isn't. And so really, like confidential EVM enables all of this. So if we look at ZK, which this isn't ZK. So with ZK EVM, you can do roll-ups of lots of transactions. You can provide proofs that something, like with Zcash, you can provide proof that you own a coin. But the contracts can't have their own secrets. So if you can keep your stuff secret, but it's not sort of autonomous. And with MPC, if you look at a lot of the bridges, so if they're doing cross-chain stuff, the MPC protocol will keep the secrets itself so that they don't get leaked. But you've got lots of network back and forth between the MPC members, which means that it's slow in practice, right? So realistically, we're using a compromise, which is inside the trusted execution environment, powered by SGX. It allows us to run contracts at almost full speed compared to the regular EVM, but the contracts can have their own secrets, which is what this is all about. So what is the different components? Well, fundamentally, we have the private computation. That means the node operator can't see anything that's happening inside the contracts as they're being executed. We've got private storage, so the contracts can store stuff, retrieve stuff. Again, the node executor can't see what's being retrieved or what's being stored. We have a built-in VRF, so rather than using an external service, you can, from a contract, say, hey, give me some entropy, I need 32 bytes, 100 bytes, whatever, and that happens instantly. And then end-to-end encryption, so the contracts can communicate with users in their browsers without the relay nodes seeing what the content is, and you can securely submit secrets to the contract without anybody seeing. So we've got a Sapphire EVM, which is our private blockchain. It's a paradigm which is secured by the Oasis network consensus, and everything inside the EVM is private. But we're going to cover some examples that show the different use cases of confidential EVM. And that's really like what to be aware of in terms of edge cases, because there are a few edge cases where it doesn't act as you'd expect it to if you're used to normal EVM. So it's 99% compatible, but you're doing privacy. So you need to be aware that EVM expects everything to be transparent. And if you want to get started, there's a bunch of links here, so the documentation, the testnet faucet, the Explorer, and a couple of demo projects on GitHub if you want to check these out. But yeah, with the testnet, you can add this to your MetaMask, and it's in the documentation there. So because it's a different EVM, and there are differences between transparent EVM and Sapphire, if you're developing with Hardhat, for example, or Foundry, you won't be able to run the full set of functionality that you'd expect to. So if you want to use the VRF, for example, if you run it in Hardhat, you won't get random data. So in order to develop on Sapphire, you're going to need to use the Sapphire dev Docker container, which will spin up a local node of the Sapphire local net on your machine. Alternatively, you can develop against testnet, and you can use the faucet to get tokens for that. So what are the differences between confidential EVM and transparent EVM? So we've got call data encryption. So that means when you submit a transaction on chain, you can encrypt the call data, and it will still be included in the transactions that are visible on the block explorer. So you'll see how many transactions have been made, the size of the call data, who it was from, the contract that it was to, the amount of gas that it cost, but you won't see the call data itself. And we've got encrypted storage. So again, the node operators will be able to see that you're storing things, see that you're retrieving things, but they won't know what the content is. And there's also a question about, can you trust the message sender parameter? So a very quick overview of this, we've got the key manager that controls access to the storage. So the confidential contract that's executing inside the trusted enclave requests a key from the key manager to be able to retrieve a single piece of storage. So unlike other networks, if there was a breach of the compute node, the attacker wouldn't be able to get the secrets for all of the storage. They'd only be able to see the specific piece of information that were accessed while it was happening. So we've set up in this way as a bit more reliable than others. Right, so let's do some examples. So I'm going to start off with a private token, which is the most straightforward use case of I want private money on my private chain. It should be straightforward. So you say I've got my transfer command, and I subtract the amount from the balance, add it to the other balance. Of course, we're not verifying what the transfer is. It's just doing the transfer itself. And you'd think there aren't any problems with this. It should be private, right? Because it's running in a confidential EVM, it's got confidential storage. But the problem is that, the compute nodes will see the I/O patterns. So as I said before, you've got encrypted storage, but you still see the access pattern. So if you subtract from my balance and add to somebody else's balance, that's going to reveal the people that were involved in a transaction. So for some cases, that's not a problem. But if you want real privacy, you have to consider this as well. Because a lot of the attacks you get against privacy systems is essentially like tracing through a graph. So if they can see this person transferred to that person, to that person, to that person, even though the balances are hidden, you'll be able to infer from that graph of transfers, who transferred to who, and infer what amount as well. So there's a really cool utility called Hardhat Tracer, which lets you see the sload and store commands. So if you're worried about this aspect of the privacy of your contract, of will this reveal information, you can use this to take out specifically the S-loads and the S-stores and see what's going on. And then that lets you develop some patterns to obfuscate that. So for example, if I wanted to switch these around, I say randomly select subtract first, then add afterwards, or add first, then subtract afterwards, then just looking at the I/O patterns, you won't be able to see, well, was it a transfer from this person to that person, or that person to that person, and vice versa. Or you could put in dummy accounts. So if you wanted to obfuscate in a similar way to Monero does with the ring signature mix-ins, you can say, of all of these accounts, I'm going to load all of their balances. I'm going to modify one with with the payment that I'm making, and then just write the same value back to all of the others. So if someone's doing analysis, they'll see, oh, there were 10 different storage stores, and I don't know which one of these are real. But in most cases, it doesn't really matter. So if you're not looking at sort of really strong privacy guarantees, then it's, there's lots of other things you can do that aren't so serious. But the second part is side channels. So because with every transaction, you can see the from, the to, the size of the call data, the amount of gas it takes. This can lead to sort of unexpected things where, the amount of gas that's used will reveal which path within the code was taken. So this can have unexpected consequences. So in this example, I'm checking, hey, does this person have an allowance big enough for the transfer to happen before it's verifying that whoever's creating whoever's performing the transaction has that amount allowed. So, yeah, I've mentioned this already. With a gas channel being public, you can start to sort of perform tests. So if the balance check is before any of the authentication, I can say, is this balance 10 ETH? And it will give one gas rating. And then I say, is it 0.1 ETH? And it will give me a different gas usage. So with this, I can perform a binary search and go through and find what the specific balance is. So in terms of like authentication and not revealing information about or the balance, you need to move authentication up to the top and make sure that no extra information is revealed through the gas side channel. So the second problem is view calls. So on Ethereum, we've got the ETH call, RPC, which simulates the transaction. And again, this is a problem, because on confidential EVM, you don't want people to impersonate you. But on regular EVM, you can simulate a call to any contract from any person with any gas amount, whatever, and it'll let you do this. So if I wanted to check someone's balance, in confidential EVM, this would be bad, because you can get everyone's balance, and of course you want the balance to be private. So we can check my balance. So if I want to view my own balance and not be able to see anybody else's balance, then you can use the message.sender parameter. But the problem there is, how do you know that the message sender is, if it's a view call, how do you know that they are who they say they are? So this is a problem that we've had to overcome by signing view calls. So you can have anonymous view calls where the message.sender parameter will be overridden to 0. So if you don't specifically sign your view calls, then the chain doesn't know who you are when you're performing a query. And this is all automatically wrapped with our wrapper with the Sapphire Paratime package. So if you're writing a client or a dApp, whatever, and you want to be able to use the message.sender parameter, you're going to have to sign your view calls. And essentially, you just wrap the provider that's provided by MetaMask or Hardhat. If you're using Hardhat, if you add the Sapphire Hardhat package in and put it in your hardhat.config, then it will automatically do that for you. But there's one problem, which is with signed view queries. If you're a user and you're using MetaMask, then every time you perform a view query, it's going to pop up and go, oh, hey, please sign this transaction, right? It's not a transaction, it's just you need to authenticate your query so that the contract knows who you are. Otherwise, it doesn't know who you are because you're anonymous. So with this, so with this, you can then verify, you can then use this to say, okay, am I allowed to see someone's balance if I have an allowance with them? So in terms of rethinking how you deal with tokens, token transfers, and the standard sort of ERC20 stuff, you can port it over, but it's not like directly applicable because of all these sort of side channels, being able to see everyone's balances. If you're doing privacy, you're going to have to modify it in a way that means that even with allowances, you're only revealing information that they know. So if I give you an allowance of 1 ether, for example, but I've got a balance of 2 ether, you don't want to reveal that I've got 2 ether when they can only spend 1. So there's a couple of other approaches in terms of like alternatives to verifying the identity of the people that are using your application. So one of those is signed queries that we've gone over, where you're signing the view call and sending it over. But you could also use like viewing keys. So I know Secret Network, for example, make you set up a viewing key. So when you create a token, or when you interact with a contract, say like a token, you set a special key that allows you to view your balance. So you can send that over along with your request to see your balance, and the contract goes, yep, that exists. But there's a problem there, which is like the chicken and egg of, in order to see your balance, you have to interact with the contract. But if somebody sends you like $100, you need gas money to set up the viewing key to see your balance. So it's really not user-friendly. It leads to situations where someone sent you balance, but you're not sure how to see it, and every time you change wallets, you have to set up new viewing keys, and it's really awkward. So like the alternative here is, you might have seen this with a couple of different NFT markets, which is like logging in to verify your account. So if you imagine on a day-to-day basis, or every time the user goes to the website, they say, please just verify your wallet. Is this you? Once you've verified signed from your wallet, just say, I'm logging in for the day, it's valid for a week. Then you pass that along with all of your view calls. So it does require you to sort of re-architect your application, or rethink it in terms of how you're querying the data. If you're performing lots of calls in batch, that's usually easier, because that won't have like pop-ups going, please sign the query, right? And then the other option is like permits and delegation. So if you want to give control to somebody else to be able to spend on your behalf, you have to think of, well, I've got allowances, but how do they know if I have the balance? Do you want like more fine-grained access control, where you can give somebody access to a specific subset of features, and yeah, it's an outstanding problem that you're going to have to think about. But anyway, if we move on, so that's like an introduction to the problems you're going to encounter if you went through the example of how do I create a private token. But next is the precompile. So precompiles are sort of the special features that the Sapphire blockchain has that are unique to it. So Ethereum has a lot of precompiles, and they're simply there because it's too complicated and expensive to do this all in Solidity. So for example, the EC add and pairing operations are very expensive, but when they're written natively, they're super cheap. SHA-256 and EC recover, also examples. And the precompiles are all documented on our website. If you want to access them from your dApp, you're going to want to add the Oasis Protocol Sapphire-contracts package, which gives you access to sapphire.sol, which is a wrapper for all the precompiles. And of course, to test the precompiles, you're going to need to use the Docker image to run the Sapphire node locally. But the precompiles we have are like encryption and decryption. So if you're running a confidential contract and the contracts can have their own secrets, then yeah, being able to generate keys is something that you'd like to have. Being able to encrypt and decrypt information is absolutely necessary. You can do signing and verification, so the contracts can generate a key and then sign for something by itself. And of course, the random number generator. So with a random number generator, it's super simple. Just request a number of bytes, and there's a personalization string as well. So you can, I don't know, add extra entropy, whatever you want to do. We also got encryption and decryption. So you can use the X25519 key negotiation to derive a shared secret between the user and the contract, or two contracts together if they want to encrypt things for each other and pass it through the user. And there's a lot of other interesting use cases. So with ECDH, just a quick overview of, because we've got the full set of curve operations inside, you can not only do ECDH, but sort of general purpose cryptography. So anything that you see that uses elliptic curves, you can do in confidence with the ECAD and ECMOL operations. So for decryption, again, the Sapphire wrapper provides some really simple, straightforward tools. So you can generate your key pair and then get the public key. And then to decrypt, of course, you derive a symmetric key. So the client passes in their public key. After previously getting your public key, you derive the symmetric key, and then you call the Sapphire.decrypt function. It's really straightforward in TypeScript. So these are all code examples. If you want to copy and paste, they do work, and it should get you started. So with signing and verification, we support a number of different algorithms. So the ED25519 curve, which is used by Monero, for example. I think Cosmos uses it as well. I think Polkadot may use a variant of it. X25519 as well, which is a slightly accelerated version of the Edwards curve. Then we also support the Bitcoin and the NIST curve. So this is the NIST curve is coming up in the next version of Sapphire, which supports WebAuthn. It supports like TLS. So if you use SSL on a daily basis, you're probably interacting with the NIST curve. And the Bitcoin curve as well, so that supports generating Bitcoin wallets, verifying Bitcoin signatures, generating Ethereum wallets, for example, and signing from them. So both signing, verification, and key generation are supported. And of course, yeah, like Touch ID is something that's really, I mean, it's slow, because you have to write it in, without support for the NIST curve, you have to write in Solidity, which costs a lot of gas, but with the built-ins, I think it's like 2,000 gas or something to generate a signature from a NIST curve, which is really cheap. So again, if you want to sign, we've got the algorithm selection, so we support a variety of different algorithms, and when you're using the Sapphire wrapper, you have to specify specifically which algorithm and variant and curve you want to use. So we support, again, a variety of different algorithms, and they're documented in the documentation. And so in order to generate a key pair, we need to provide the entropy for this. So this is essentially the secret key. So if you're generating a secret key, get some random bytes, give it to the generate key pair, and it will give you the public and the secret key, which you can then use to sign from. And to verify, it's, again, really quite simple. If you use the Sapphire wrapper to perform the verification and pass in public key, the digest, and the signature. And there are different variants of the signing and verification algorithms either take like the pre-hashed message or they take the raw message itself, and it depends on the protocol, on the algorithm you're using. But so this is all like the necessary stuff that we need to understand, and in order to be able to do the more interesting stuff. So like integrating with Web 2 is like a difficult topic with like the Web 3 industry as a whole, because you've got like the Web 3 way, then you've got the Web 2 way, and like really like Web 2 is like there's no plugins. It's super easy to use. Your grandmother uses it every day. It's on every device, so you don't have to, you know, if your TV, for example, has a browser, most likely if it's a smart TV, like refrigerators, but they're all using usernames and passwords. So you've got like the Web 2, which is all usernames and passwords, the Web 3, which is all, you know, key pairs and signing, and they don't sort of mesh well together. But with confidential contracts, you can have end-to-end encryption. So Web 2 assumes that with SSL, you can securely submit stuff to the server, you trust the server, and if it's a contract running in a trusted enclave, then you can take the trust out of Web 2. So for other use cases like you know, OAuth, S3, JWT, you can generate signed cookies, for example. But you also have to be aware of like brute force attacks. And then, because on Web 2 you don't assume that everything is private, it's a problem. So hopefully if we look at Web 2 integration with Sapphire, because it's got confidential contracts, this should help the two worlds sort of mesh together a bit better. So I mean, the first example that came to mind was TOTP. So this is one thing that you can't do on Ethereum, because in order to generate like the two-factor code that you use in your authenticator app, the contract needs to know the same secret as you. So this is something it's really annoying that it's on every device, or every Apple and Android device. You can download the authenticator. It's used by loads of services, but you can't use it on Ethereum, which is annoying, right? So if I wanted to give my manager a TOTP code, and if I want to perform a transaction and I need his authentication, so his authorization, it's easy to phone up and say, hey, can you give me the TOTP code? I need to make a transaction. And this sort of model that we're used to working with is more complicated with the Web3 stuff. Because, again, your managers might not be Web3 natives. You might have to, they might be on holiday, they might not have internet. But with TOTP codes, this is really straightforward. So another example I said was the Amazon S3. So loads of people use IPFS, and now we've got like the IPFS pinning services where you can make sure that your files don't disappear over time. But the rest of the world, they use Amazon S3, Google Cloud Platform, and their storage solutions, where you might want to be able to provide an S3 bucket and let people upload big files to it and generate a secure link that you can give to the person that allows them to upload one specific file. Or if you wanted to do confidential NFTs, for example, if it's stored on S3, you can set up access controls. So upon purchasing the NFT, I can say, hey, give me the link for the full file, and it will give you a download link that's limited for 24 hours, for example. Because the contracts have the confidential data, they can keep the S3 secrets, they can generate links, and it opens up some interesting options. The other example is JWT. So if you've ever dealt with like REST frameworks, APIs, integration, loads of people use JWT, and it's another sort of pervasive Web 2 standard where this is just how it works, because they assume that the server has secrets. They assume that somebody's there going to be generating keys, signing stuff for you. So imagine like a smart contract that can generate access control. So if you want to sign up for online, on chain, you want to sign up for some API, and you want to get an access token to perform API calls, the token, it can do this now. So you don't need to have your Web 2 infrastructure be like aware of Web 3. You just have the contracts that work with your existing infrastructure, but can control access and can do stuff in return for money or whatever kind of integration you want to do. So this brings up the topic of like sort of gasless meta transactions, which I know is relatively popular at the moment. And that's essentially like towards the like contract autonomy. If you've got the signing, you've got the key generation, you've got the confidentiality, and you can generate Ethereum-compatible wallets. This means that you can sort of sign for transactions, which is interesting. So, for example, you've got a user interacts with our signing contract, and we say, hey, can you create a transaction for me? So the contract, using its key pair, will sign a transaction where maybe the user can control some parameters, or you're doing a swap, or it's acting on your behalf. It gives you the signed transaction, which you then submit back to the contract. Well, in this example, I just created a small function where it generates a transaction that calls its own function. So like, think of like anonymity. If you've got the contract that's signing for you, you don't know who invoked the contract to get the signature, because all of the signatures come from the same signer. And of course, this works on other chains. So you could have the contract on Sapphire generate signatures, push them over to Ethereum, and everything looks like it's coming from the contract, which abstracts it away from the individual users performing the actions. So yeah, this is included in the Sapphire contracts package. So you can generate an Ethereum key pair and then use the EIP155 signer to construct the transaction and to sign it with your address and your secret. And this is just a super simple example of how do I generate my key pair. I import the Ethereum utils.sol file, and then I perform the signing of. So this is signing just a general message. So you could implement EIP712, or you could sign arbitrary stuff, and it can do that. Or you can sign an EIP155 transaction, so that's compatible with most Ethereum compatible networks. So Ethereum, BSC, Polygon, etc. And the problem here is that the contract doesn't know like the gas price. So if you're signing a transaction on a remote chain, you need some way of knowing, okay, so what's the account nonce? What's the sequence? Because if the contract's like autonomous and it's in its own sort of little isolated enclave, and it doesn't have oracles, so how does it know that the gas price you give it is not going to just take all of its gas paying balance away? Or how do you know that someone's not going to do something malicious or deliberately submit transactions with low enough gas price that are going to stop the contract from submitting any more transactions, right? So this is something you have to look out for. I mean, if it's your own contract, it's your own funds, and you're using it to like delegate signing to some kind of multi-factor authentication, then you can provide whatever gas price, whatever nonce you want, and it's up to you to decide. So we actually got a demo of this where we figured that one of the problems was you can't expect people with so many different chains to, if you want to use private voting on Sapphire, you've then got the problem of everybody needs to get some gas to pay for the transaction on Sapphire to submit their votes. So if you want, I can give you an example super quickly of essentially the secret ballot. So I'm logged in, I vote. It pops up a notification and says, this is proposal, the voter, the choice is McDonald's, using EIP712. And then this is one thing you'll run into, which is view call. So it's signing a view call, which is sort of like a bad UX problem of, because you've got the signer attached to the provider, whenever it performs a view call, it will ask you to authenticate it. But so we're signing something, but we're not submitting a transaction. We're not using any gas, and I actually have 0 balance here. So I sign this, and behind the scenes, the contract's generating the transaction to submit your vote on chain. So it's like a sort of gasless meta transactions. This brings us into like account abstraction. So with the contracts that have their own secrets, they can manage keys for you. I've another demo I've got set up, which is WebAuthn. So we've got like a full like account abstraction example where using like a YubiKey or using like passkeys on your phone, you can get the contract to sign messages for you. So this is where, like a hardware security module, you don't actually have the secret key on your device or any other thing. So only if you log in through using WebAuthn or passkeys can you get the contract to sign on your behalf. So in terms of like customizable logic and both TOTP, WebAuthn, these can make some really interesting situations where you can give the contract control. So if you want to have spend limits of, say, $1,000 a month, you can have the contract only sign transactions for up to $1,000 per month before it stops completely. And so because it's signing real transactions, this means you don't necessarily have to have the contracts deployed on every single network that you want to operate on. You could have a single contract on Sapphire that signs transactions on loads of different networks. So I could have a contract on Sapphire that authenticates me to sign on Ethereum, and it will do that for you. And I missed an example there. So the next problem we have is we'll cross-chain. So like Sapphire exists in isolation, so we need a bridge, basically. And this lets you keep some of the stuff that you need to be private on Sapphire, so you don't have to migrate your whole application onto Sapphire. And because it's a message passing bridge, you could send a message from Ethereum to Sapphire and say, this user wants to do something, please handle this for me. And they want to do it in private. The user will go and do something in private, and then submit the result back over to Ethereum with whatever the result is. Which means you, again, with smart privacy, you get to do the private stuff in private and the transparent stuff in public. So you don't have to rely, if you want your assets to be on Ethereum or on Binance where it's secure, that's where they live, then you can do that and move, say, a part of your DEX over to Sapphire, or, I don't know, it's interesting. So this is fairly straightforward. Again, the Sapphire contracts package includes everything you need. And under the hood, we're using the Seller IAM bridge to pass messages to all the chains they support. And you just need to use opl.sol. So we've got the user, which submits the request to the dApp or the dApp plugin, which sends it to the message bus, which emits an event, which is picked up with the State Guardian network. So this is Seller's sort of multi-chain verification system. The executor sees that the State Guardian network has authenticated this message, which submits it to the message bus along with the State Guardian secrets on the destination chain, which will then invoke the dApp plugin. But who runs the executor it's not a gasless solution, so you have to run an executor yourself or get in touch with Seller to run an executor for you. It's fairly straightforward. So you post a message, which can be anything, and we're using messages and the methods. So the methods like the message destination title. But the two contracts are linked to each other. So I'm going a bit fast now. So the two contracts are linked to each other. So you've got one contract on the enclave and one contract on the home network. So you have to provide the addresses of each other to each other when you construct them. And you can predict what the addresses are, can be ahead of time, so it's not too much of a problem. And essentially, you register your functions that you want to be callable in the constructor. So you want to register your endpoint, say the example, the Sapphire example endpoint, which then on Binance Smart Chain you can say, invoke this, it will post the message along with the arguments, which will then be called, and you can return success or failure, depending on the status. But really, I want to get on to some of the more interesting cases, which is like roll-ups and scalability, which is, loads of people are doing ZK roll-ups, and that allows you to compress the computation of lots of different things, and then bundle it up into only the information that you need to be transmitted. So the account differences, so the differences in the balances, or you don't have to include all the signatures because you know that the transactions are valid. But on Sapphire, there is some interesting things you can do here. So because the ETH call is free and the contracts have access to private state, that means that you can get the contract to sign stuff for you. So one example is you could provide the contract's previously signed output to the contract again and get it to sign that along with the next piece of work. So the example here is it will allow you to condense all of that information into a single signature provided by the contract. So if we look at a Bitcoin-like client, for example, if you want to run a Bitcoin-like client in view calls alone without modifying any state, then you can pass all of the blocks one by one to the verifier contract, which verifies the proof of work is cumulative. It verifies the consensus algorithm, and it provides you provide it the previous proof of the verifier client to it, and then any signature that it outputs, you can verify that, oh, this has been running for 2,000 blocks, the proof of work is this, rather than having to submit all of the blocks to back again. So an example is if you want to synchronize the Bitcoin Lite client on Ethereum, you have to set up the verifier, then you have to shuffle in all of the blocks, and you have to keep providing the blocks for it to verify that the block hashes you're providing are correct. But if you run this on Sapphire, you could have the Lite client on Sapphire running, and then if you trust the signature of the Sapphire contract, then you can have a Bitcoin Lite client on any other network as long as it trusts the signature, without having to relay all the blocks again. So there are lots of other examples, if you want to talk to me about this, of where rollups on Sapphire with confidentiality can let you do things that are just not really possible in a gas-efficient way on other chains. So, I mean, some of these examples are like shortcutting messages. So if you think of a protocol where the contract's going back and forth and back and forth, you could use view calls on Sapphire to, say, verify the state, and because you can pass information back and forth and back and forth, you can have an entire round trip going on between you, maybe 3 or 4 other parties, with the contract encrypting data to pass back to it that can be securely passed through other people's hands without having to worry about it being tampered. So if you can do this without having to modify the state, then it's basically all free. And it's only costing you gas when you need to start making modifications to the global state. So if you think of like the typical 2 or 3 phase commit process, you can condense this down into like one step with Sapphire, where because it can mediate, it can generate keys, it can encrypt information, you don't need all of these round trips. So that's, in terms of like scalability, instead of waiting for your transaction to be mined and the limit being the number of transactions that can make state modifications at the same time, instead you can spread your queries across all of the different view nodes and you get scalability to the relative to the number of nodes in the system versus relative to the number of state modifications it can make. So I should also add that we're running a hackathon at the moment. So it's started already, and it's going to be running up until October the 4th. And there's $30,000 in prizes across 4 different categories, with 25 grand in follow-on support and grants. And there's going to be free audits for successful projects. So the 4 different categories are, you've got the best app on Sapphire, so it's anything that's native to Sapphire that uses the private storage, the RNG, encryption, signing, etc. There's also the best app that uses OPL, so if you have an application already that you need to make some bits private, you can use OPL for that and submit it to the hackathon. There's also like the best use of Sapphire for scalable privacy, so what I've just said about rollups, it's also confidential, right? So you can do lots of things in private very quickly and then submit the results to, say, Ethereum or Binance, and that would be a huge speed up versus doing them all on those chains individually. And then tutorials and standards. So I've learned that if I'm doing a hackathon and my project doesn't quite work, I can turn that into a tutorial. But there's also the opportunity for standards where there's lots of stuff that needs reimagining because of the privacy aspect, because of the confidentiality, where like the token standards, you can use them, but they won't be private. The NFT standards, like, are there any options for confidential metadata? This is just lots of some examples there. But yeah, there's 25 grand in follow-on support for runners-up and winners. And yeah, that's the link for that. And thank you, that's me done for today. So I think we've got 15 minutes left. So if anybody has questions, or if we can sit down, or whatever you want to do, I'm happy to answer any questions you have. Yeah.
Thank you.
Oh, can you get the microphone? Sorry.
Thanks. It was heavy workshop in terms of information.
Yeah, I'm sorry about that.
No, it was super helpful, and you touch on a lot of things that at least our team is thinking about and struggling with, at least on alternative chains.
Yep.
My question is super general. I just was wondering, have you seen people build non-financial applications?
Yeah, so in terms of the applications out there, like finance obviously is one of the main use cases, simply because it's so integral to everyday use. But outside of that, it's, well, I mean, I'm honestly struggling to think of use cases that don't involve DeFi or don't involve finance in one way or another. Simply because, you know, without any money involved, the stakes, you have no stakes. So there's less need for trust, less need for confidentiality. But you can look at voting. So if you want to keep the votes private while the vote is active. So in most elections, your vote is private forever, you know, and you can't see people's votes. But with Web3, that often ties back down to how do we spend money and how are we voting on that, right? Yeah.
I was thinking of voting examples or personal data management.
We were looking at like password managers. So being able to, say, delegate access to your passwords or a specific password for an amount of time. That's something that's come up. So I think we should wrap this up. Yeah.
No more questions.
Cool. Thank you for coming today. And please come and talk to me, and we can talk about the hackathon, and if you have any interesting ideas, and point you in the right direction. Okay, thanks, guys.